All right, I'm going to go ahead and redo the recording since the audio turned out really bad on the first one. Like I said, it's going to be a long one, so let's get into it. This is How Math Became Reality, a comprehensive look at the classical and experimental evidence that's put forward for relativity theory. You could find me on YouTube at space_audits or on Telegram under the same name at space_audits or on Discord, Alan hashtag 3658. Oops, wrong button. All right. Abstract. Relativity theory has been around for over a century now, and to this day, acolytes in support of the theory have completely surrendered their faculties to equations and concepts that they don't fully understand or care to. The classical proofs of relativity are often cited to handwave dismiss any criticisms of the theory, despite not even being able to account for what spacetime exactly is. This presentation attempts to clarify on what spacetime is and take it a step further. I will make the claim that spacetime has to be a physical entity if any curvature thereof was to be responsible for the physical effects that are attributed to it as proof of the theory. Classical proofs of relativity theory, the perihelion precession of Mercury, deflection of light by the sun, gravitational redshift, and miscellaneous indirect confirmations of the theory such as time dilation. If relativity theory were to supersede the Newtonian framework, it would need to prove that spacetime is a physical entity and has a mechanical cause and effect relationship with how it interacts with physical objects. Here we will examine the historical narrative and experiments that are put forward to support the physicality of spacetime. We got some prerequisite information here that we're going to go over before we get into it. A degree is a unit of angle measurement equal to 1/360th of a full rotation. If you look at 1 degree and 2 degrees, and then you go in between there, if you break that into 60 sections, you have 60 minutes of arc. And for every minute of arc, there's 60 seconds in a minute. So you can break it down even further, and you can get down to 1/3600th of a degree. And then if you times that by 1,000, you get into the milliarcs at 3.6 million. 1.36 millionth of a degree, and then you can times that again by 1,000 to get into the micro arcs, which is 3 billion 600 millionth of a degree. But we're going to be in this range right here, so I'm not really too concerned with these. I just wanted to show you how the full system works. Prerequisites: spacetime, metric, and curvature tensors. In relativity theory, the use of a metric tensor or curvature tensor is a differential equation that's derived from Einstein's field equations that are used to describe the geometry and properties of spacetime. These equations or solutions are used to model the effects of mass and energy on spacetime, causing it to curve. And through that curve, the motion of celestial objects in a gravitational field can be generally described. Commonly used metric tensors: the Schwarzschild metric, used to describe spacetime outside a spherically symmetrical, non-rotating, non-charged mass, such as a black hole, describes the curvature of spacetime due to the mass of an object and the motion of another massless object traveling through the curvature of spacetime caused by the gravitational field of said object with mass. The Kerr metric, which is another black hole metric, it's kind of an offshoot of the Schwarzschild, but anyway. So this one's used to describe spacetime outside a spherically symmetrical charged mass that's rotating, and the distinction between those two is rotation and what's the other one? And charge affect the gravitational field, so gives slightly different answers. And like I said, offshoot of the Schwarzschild, there's the FRW metric. This is a metric tensor used to describe the large-scale structure of the universe in the framework of cosmology. It assumes homogeneity, isotropy of the universe, and describes the expansion of the universe as a function of time. What does all that mean? Who knows, honestly. Curvature tensor. Equations used to describe the curvature of spacetime, which is related to the distribution of mass and energy of the universe. The Riemann curvature tensor and the Ricci curvature tensors are the two most common ones that are referred to when they talk about, the solar system and the universe and all that. Let's see. So yeah, if we make assumptions, we can calculate it. That's kind of the motto that they have, because as we're going to see here, well, we'll see later on when I break down what a Schwarzschild metric is, you'll see exactly what that means. Prerequisites: spectrographs and spectrum shifts. A spectrograph is used to determine the spectrum shift of light by analyzing the light emitted by a star splitting it into individual wavelengths. And you can also use it to analyze the light from any light source, really. But we're talking about stars and starlight here. The spectrum light is split into a diffraction grating or a prism and then recorded using a photographic plate. And this is just describing the two different methods that are available for splitting the light wave. And then to record the data in the time that we're talking about, they took photographic plates and made snapshots, and then they would color in a spectrum shift or the color spectrum manually on paper and then compare it. And this is what we're looking at here. You can find out more about how they did that from this place. Total Solar Eclipse by the Pogson. Your boy Poggy, huh? All right. So, and here's a YouTube video if you want to learn more about spectroscopy and how it works. Very useful stuff. Standard observational conditions. So back to these small angles here that are, small units of measurement here, the arcseconds and arcminutes. So let's see what dude has to say about the ability to observe fine measurements from our terrestrial perspective. At a high power, viewed from the bottom of our ocean of air, a star is a living thing. It jumps, quivers, and ripples tirelessly, or swells into a ball of steady fuzz. Rare is the night at most sites, where any telescope, no matter how large its aperture or perfect its optics, can resolve finer or details finer than 1 arcsecond. More typically, at ordinary locations, is the 2 or 3 arcsecond seeing or worse. That's from Mac Roberts' 1995 Sky and Telescope magazine. All right. So now that we got a general idea of what we're going to be looking at here, we're going to get into the classical proofs of relativity theory. The first one being the perihelion precession of Mercury. The perihelion precession of Mercury and why it's important to relativity theory. The perihelion precession of Mercury is a gradual shift in the position of Mercury's closest approach to the Sun over time. In 1846, Urbain Le observed and recorded the perihelion precession of Mercury as it orbits the Sun. His calculations ended up estimating that Mercury would precess by about 5,600 arcseconds per century. Many years later, Newtonian mechanics and relativity theory faced off to account for the precession. Here are the results. Actual observed precession, 5,600 arcseconds per century. Newton was able to account for 57 seconds of arc per century. And relativity theory came in hot with a full 5,600 arcseconds on that quote unquote prediction. Now, they talk about these things like they're predictions, they're postdictions. The observations of Mercury's perihelion precession was made way before Einstein came along to match the exact amount. So anyway, it's kind of little misrepresentative to call it a prediction. So anyway, Newton's mechanics were off by 43 arcseconds per century, while relativity theory, using a modified Schwarzschild metric, Einstein was able to match the observed 5,600 arcseconds per century. Getting people to accept this calculation as proof of general relativity was crucial of giving physical solutions using mathematical concepts. Continuing with the presentation, we'll cover the math used in the calculations and cover other possible explanations for the precession that were shelved in favor of bending spacetime. And we have, misleading it, covered that. Okay. Continuing on with the presentation, we'll cover the math used in the calculations, and we'll break down what these equations mean. All right, so here we're going to look at the Schwarzschild metric, or the Schwarzschild solution, or as I like to call it, the imposed ideal conditions to reify the spacetime solution. So this is what the metric looks like right here, and we'll break down what each of these terms means. So we have ds squared. That's the metric tensor that describes the geometry of spacetime and general relativity. We have this little fun piece right here. This is the factor that describes the time dilation and the gravitational redshift experienced by an observer in a gravitational field due to the curvature of spacetime. So whenever they talk about matching predictions and we predict this much amount of redshift, this amount of time dilation, this part of the calculation is where it comes from. So we got dt, this is the time coordinate, which measures the elapsed time between two events in space-time. I got this fun guy right here. This is the factor or the reciprocal of the above factor and describes the describes the effect of gravity on the radial coordinate. And we'll get to what the radial coordinate is at the end. And we got your boy d theta represents the change in the polar angle between two events in space-time. We got d phi, which represents the change in azimuthal angle between two events in space-time. R, which is your radial coordinate, which is used to measure the distance between an event and a central mass. G, your gravitational constant, which relates to the curvature of space-time, to the mass of the object. M, you got the mass of the central object, which causes the curvature of space-time. We got your speed of light in a vacuum for C. We got sin squared theta, which represents the square of the sine of the polar angle theta, which appears in the term for the azimuthal angle d phi squared. But what does it all mean, you ask? The Schwarzschild metric is an equation of imposed ideal conditions that are used to generally describe how an object moves through another object's gravitational field. For instance, take the Sun and Mercury, for example. The metric would calculate the Sun's mass and its impact on space-time curvature. In general relativity, if the Sun's spinning and if it has any charge, right, that's going to increase the effect that it has on space-time. So the Schwarzschild metric assumes that the Sun, in this scenario where you're trying to calculate how the Sun would impact the orbit of Mercury, you would say that the Sun is a stationary, non-rotating, non-charged mass that has no charge potential. Oh, sorry, I already said that. And it would just disregard all that. And then it would further say that Mercury, in fact, also has no mass. Because if Mercury had mass, that would impact the effect of the space-time curvature, and they wouldn't be able to, quote unquote, accurately match or predict Mercury, post prediction, really, but predict Mercury's orbit because their coordinate system would be off. So it's really just it's just a really neat way to hypothetically calculate something. But they've taken it a step further and said that they've found that space-time is is an actual thing that curves and things travel on, right? So we'll get into all that as we progress. So that is the Schwarzschild metric. Very fancy way of saying that there's still no solution for the three-body problem. All right. Other theories and explanations for the precession of Mercury. Paul Gerber was a physicist who proposed a velocity-dependent potential correction in 1898 to explain the perihelion precession of Mercury. His theory was very simple and effective, and he correctly accounted for the observed perihelion precession of Mercury. His equation was just this right here, nothing too fancy. Not quite a Schwarzschild, if you know what I'm saying, but this'll do, right? That'll do, donkey, as they say. While this equation was able to accurately match the observed perihelion precession, Gerber was criticized for not providing a consistent underlying principle or explanation for why his correction should be made and added to Newton's gravitational laws, even though it resulted in the correct number. Because Gerber's mathematical explanation wasn't based on principles or having a physical mechanism to explain why it needed to be added, his solution was ultimately rejected. And here's a couple arguments that he could have made. Finite speed of light, which means that the gravitational force between two objects would not be instantaneous, but would take some time to propagate. This would delay the gravitational force experienced by Mercury, which would affect its orbit. He could have also invoked the equivalence principle, stating that the effects of gravity are the same as those of acceleration. Gerber's correction could have been seen as a way of considering that Mercury is in a constant state of acceleration due to its orbit around the Sun. Continuing on, it should be specially noted that Gerber's explanation, while mathematically sound and widely accepted to be an accurate way to account for the precession of Mercury, the criticisms of his explanation come from the fact that he didn't have a physical mechanism or principled theory as to why he should add the correction or how it was derived from Newton's original theories or equations, sorry. On those grounds alone, even though the math worked out, his solution was rejected. Einstein is allowed to add new terms to metric tensors, swap out tensors, using tensors that don't even have physical meaning to the phenomenon they're trying to explain, i.e., describing the sun as perfectly symmetrical, non-rotating, with no charge, and Mercury counted as no mass in a perfect vacuum, with no other forces acting on it, so that it can travel in a geodesic around spacetime curvature, aka move in a straight line that's really curved. These egregious violations in tailored specific metrics and equations are overlooked because Einstein's theory has a story to it. Spacetime, a concept that can bend, warp, contract, or expand. If you want to explain a phenomenon that your theory can't explain, no problem, just swap in a different metric or add terms to it to describe how spacetime is being impacted, in a different way. That's really all you have to do. And with protection like that, Einstein and relativity can't lose. Mercury Perihelion Precession conclusion. Theories and solution derived from principles often do not match observed reality, and the math used by Einstein has been criticized as manipulated to produce the desired results. Other competing theories that exhibit the same issues are dismissed, while Einstein's solutions are not held to the same standard. Modern physics and cosmology allows for changes to be justified by simply stating that they believe space-time acts differently under certain conditions that they impose on it mathematically. And then because the math works out, they say that's how space-time is therefore changed. However, space-time is not a physical object that can be measured, so we must trust the mathematical description and the presupposed behavior under certain imposed conditions, even if they can't physically be verified. So we're going to move on to the deflection of light rays. Deflection of light rays, or gravitational lensing. Newtonian physics and Einstein's relativity theory make two different predictions for the deflection of light rays. Einstein's theory of general relativity predicted that light would deflect by a gravitational influence due to the curvature of space-time caused by mass and energy, while Newton predicted that light would bend also, but by half as much as what was predicted by relativity theory, and due to a different mechanism. In Newtonian physics, gravity is considered a force in the traditional sense and described as a mechanism of attraction between two or more masses. Newton thought gravity would act on light as if it were a physical particle. In Einstein's relativity theory, gravity is not considered a force in the traditional sense, but rather the curvature of space-time caused by massive energy. Differential equations called metric tensors are used in general relativity to provide a geometric interpretation of gravity in which the presence of matter and or energy causes curvature in space-time that dictates the motion of objects in a gravitational field. Einstein's concept of curvature in spacetime usurped Newton's mechanical attraction force as the dominant explanation of gravity. Arthur Eddington's expedition to prove relativity theory by way of gravitational lensing. May 29, 1919, British astronomer Arthur Eddington led an expedition to the island of Principe off the coast of West Africa during a total solar eclipse. The purpose of Eddington's expedition was to determine the accuracy of three theories regarding gravitational influence on starlight, causing a displacement of a predicted amount. The theories that he was trying to confirm were as follows. One, that there would be no gravitational influence on light, i.e. no displacement, an effect in accordance with Newtonian law of 0.87 seconds of arc, or one determined by Einstein's theory of general relativity, which predicted 1.75 seconds of arc of a displacement. The expedition aimed to distinguish between these possibilities. The data that he collected would be used just 7 months later to solidify the direction of physics and cosmology for the next 100 years. Arthur Eddington's data. Unfavorable weather conditions rendered almost all the photographs worthless. As time went on from his initial discovery, Eddington's story changed to bolster his conviction in the evidence or lack thereof. Eddington wrote Fowler in 1919 before returning from his expedition. June 3, 1919. The cloudy weather upset my plans and I had to treat the measurements differently from the way that I had intended. Consequently, I have not been able to make any preliminary announcements of the results, but the one plate I measured gave a result agreeing with Einstein. June 1919. I secured 16 photographs, but only the last 6 was the sky clear enough to show any stars in them. I only got between 3 and 5 images, and as the sky was generally only clear on part of the plate, or was only clear on one part of the plate at a time. The stars secured on the plate are badly distributed. However, one plate has some evidence of deflection in the Einstein sense, but the plate areas have yet to be fully determined. 1920. The results from the plate gave a definite displacement in good accordance with Einstein's theory of relativity, disagreeing with the Newtonian prediction. Although the material was very meager compared to what had been hoped for, the writer, who it must be admitted was not altogether unbiased, believing it convincing. And last one, according to Professor A. Vibert Douglas, 1957, who wrote Arthur's biography, and later, this is a quote from Eddington, in later years, Eddington referred to the findings as the greatest moment of his life. Eddington data continued. Throughout different stages in his life, the way Eddington viewed the data extrapolated from 2 of the 16 plates changed severely. He went from being disappointed at the results to believing them regardless of the uncertainty and accuracy of the data. Despite the meager results, he recounts it as the greatest moment of his life. He went as far as to backtrack his story about the poor star distribution, later claiming in a paper titled Dyson and Others in 1920 that the 5 stars shown on the 2 plates from Principe included all the most essential stars, and even further suggesting that the clouds may have been beneficial by preventing overexposure from the brightest stars. So this dude got high on his own pictures and never looked back, in my opinion. The controversy of the accuracy and merit of the data collected is the mainstream point of contention in the story. However, there is a more subtle conversation being had over an entirely different aspect of the eclipse data that proves to be devastating to the narrative that the 1919 eclipse supports relativity theory. Using the Observatory, volume 42, pages 389 to 398 as our guide, we'll meet the men who got together on November 6, 1919 and came to the conclusion that Newton was out and Einstein was in. These are the men who gave the go-ahead to turn math into reality. Quotes from the joint eclipse meeting. Sir Joseph Thomson. Sir Joseph Thomson, President of the Royal Society. Sir Joseph Thomson, President of the Royal Society. It is difficult for the audience to fully weigh the meaning of the figures that have been put before us, but the Astronomer Royal and Professor Eddington have studied the material carefully, and they regard the evidence as decisively in favor for the larger value of the displacement. If the theory is right, it makes us take an entirely new view of gravitation. If it is sustained that Einstein's reasoning holds good, and it has survived 2 severe tests, then it is the result of the highest achievements of human thought. The weak point in the theory is the great difficulty of expressing it. It would seem to me that no one can understand the new law of gravitation without a thorough knowledge of the theory of invariance and of calculus of variation. One other point of physical interest arises from the discussion. Light is deflected in passing near large bodies of matter. This involves alterations in the electric and magnetic field. This again implies the existence of an electric and magnetic force outside of matter, forces present unknown, though some idea of their nature may be got from the results of this expedition. Continuing on, we have Eddington introducing his thoughts on the matter. We know that momentum is carried along with the path of a beam of light. Gravity in acting creates momentum in a direction different from the path of the ray, and so causes it to bend. For the half effect, we assume that gravity obeys Newton's laws. For the full effect, which has been obtained, we assume that gravity obeys the new laws proposed by Einstein. This is one of the most crucial tests between Newton's laws and the proposed new law. Einstein's law has already indicated a perturbation causing orbit of Mercury to resolve. That confirms it for relatively small velocities. Going to the limit where the speed is of that of light, the perturbation is increased in such a way as to double the curvature of its path, and that is now confirmed. This effect may be taken as proving Einstein's law rather than his theory. It is not affected by the failure to detect the displacement of the Fraunhofer lines in the Sun. If the latter failure is confirmed, it will not affect Einstein's law of gravitation, but it will affect the views on which the law was arrived at. The law is right, though the fundamental ideas underlying it may yet be questioned. One further point must be touched upon. Are we to attribute the displacement to the gravitational field and not to refracting matter around the Sun? The refractive index required to produce the result at a distance of 15 arcminutes from the Sun would be that given by gaseous pressure of 1 over 60 to 1 over 200 of an atmosphere. This is of too great of density considering the depth through which the light would have to pass. Fraunhofer lines are a specific absorption line that's present in the spectrum of sunlight after it has passed through the Earth's atmosphere. They are caused by the absorption of the elements in Earth's atmosphere such as iron, sodium, and calcium. All right, continuing on, we got Frank Watson, Astronomer Royal. Frank Watson Dyson, Astronomer Royal. To the right, 2 photographs from the eclipse expedition were put forward as evidence of general relativity. When presenting the photographs, Dyson gave a speech explaining the purpose of the expedition, which I will condense down to his closing statement and his conclusion on the data. And these are the 2 pictures presented. The day of the eclipse opened cloudy but later cleared, and the observations were carried out with almost complete success. The plates were measured at Greenwich immediately after the observers returned. Each plate was measured twice by Messrs. Davidson and Ferner, and I am satisfied that such faults lie in the results are in the plates themselves and not in the measurements. After a careful study of the plates, I am prepared to say that there can be no doubt that they confirm Einstein's prediction. A very definite result has been attained in the deflection in accordance with Einstein's law of gravitation. Continuing on, Professor Alfred Howler, President of the Royal Astronomical Society. The quantity looked for, I may say, is 100 times the probable error of the measurement which can be made with the large spectrographs now employed in such inquiries. Evershade has also examined the light from the Sun away from the Earth by photographing the spectrum of Venus when on the further side of the Sun. Gravitational displacement, if they exist, should appear in all parts alike, but he finds no such displacement on the other side of the Sun, though he does get a slight displacement on the near side. It is very desirable that these spectroscopic tests should be carefully repeated. Professor Frederick Lindman. As to the theory itself, I must confess that the fact that it's always presented from a purely mathematical point of view seems regrettable to a mere physicist. No doubt that the present form is correct and even elegant once one has become familiar with the notion. I cannot believe, however, that a profound physical truth cannot be clothed in simpler language. To put the theory in the form of curvature in a space-time manifold seems to me much simpler than the tensor presentation. Cannot Professor Eddington translate his admirable treatise from the tensor notion into some such form? All right. And continuing on. Professor Hugh Frank Newell. May I add my congratulations to the extraordinary success of the observations. I feel that the Einstein effect holds the day, but I cannot yet give up my freedom of mind in favor of another interpretation for the effects obtained. If Einstein had not existed or had not predicted the deflection, we might have had a similar experiment made to test the presence of an extended atmosphere around the Sun, and we could have argued the results back to the hypothesis. Think for a moment of the fine prominence that was seen on the day of the eclipse. It was followed by Evershade for a rotation and a half. Matter was expelled outward in the course of movement, as we know from the sequence of photographs secured with the spectroheliograph at Cambridge on the day of the eclipse. And yet this matter at different high levels goes around the Sun, not with gravitational velocities, but with the same velocities as holds at the lower levels of the spot. It is, I know, a cheap criticism to make a qualitative suggestion in opposition to a quantitative result, but I feel that I want to keep an open mind in the existence of matter in a gravitational field, and the electric forces are acting simultaneously in an unknown relation under the conditions which admit the existence of an extended corona. It does not carry much weight to me, or with me, that that when it is urged that to explain the deflection in terms of refraction, that the medium having a density of 1 over 200 or 1 over 40 of the terrestrial atmosphere would be needed. But we have to do with the possible extended solar atmosphere at very high effective temperature where we have to do with a possible extended solar atmosphere at very high effective temperatures, almost certainly in part controlled by electric as well as gravitational conditions existing in it. And who can say what its refractive index properties may be? I prefer to keep an open mind about the interpretation, but I wish in conclusion to add my heartiest congratulations to the Astronomer Royal and the observers on their observations and the results obtained. So we're getting a little bit of pushback here, and dudes introducing to the topic that there should be spectroheliograph results in conjunction with the eclipse observations, but they're nowhere to be found. All right, so we'll continue on and learn a little bit more of this. All right, continuing on. Professor Frederick Lindman. Might I say one word? Have we not evidence of motion of comets passing near the sun? That matter outside of the sun is distinctly diffuse. The comets suffer no noticeable checks in their path. So dude was counter-arguing what they were saying about there possibly being an extended corona that's causing the displacement. He's saying that, well, if comets go by and they're not, the trails aren't displaced, then that theory's bunk. So that's what seems to be a pretty good rebuttal. Let's continue. All right, Dr. Silberstein, aka Whitsett's great-grandfather. But in spite of what the president said, I believe this result to be essentially an isolated fact. There is a deflection of light rays, but it does not prove Einstein's theory. It cannot logically be deduced from his theory of gravitation as a gravitational effect in absence of the spectroscopic results. And as far as we know from St. John's and Evershade's observations, the predicted shift in the spectrum lines of an amount exceeding almost 100 times the probable error of the modern spectroscope, as Professor Fowler had just told us, is not obtained. Professor Lindman's attempt to explain the obstinate nullity of the effect of the motion of the luminous gases and the line of vision is not satisfactory, for St. John was well aware of such complicating circumstances and therefore purposely observed as many as 43 lines at the sun's center and almost as many as 35 at the limb. Now, we cannot well assume that the gases move everywhere toward it or away from us only to suit Einstein's theory, i.e. just to compensate for his theoretical shift. As I have already pointed out on another occasion, if there is no spectral shift, Einstein's coefficient, the way that he describes space-time curvature, which is entirely responsible for it, must be unity. And if we go back to the differential equations, Einstein's field equations, we shall see at once the other coefficient in his well-known approximate solution becomes unity at the same time, being, and then he rattles off some math here, which I'll go over in a second, so that the world element reduces to, and then he spits out some more math, which we'll cover. And since the equations of motion are always given by Greek letter ds equals 0, we can ultimately see the spectral shift is absent. Einstein's theory not only does not give such refinement of planetary motion as a secular motion of the perihelion, but even in the ordinary Newtonian or Keplerian motion. In short, the orbits of the planets would be straight lines and the planets would be moving along them uniformly despite the sun's presence. The theory stands or falls on the correctness of the results of Evershade and St. John. It is unscientific to assert for the moment that the deflection, in reality, which I admit is due to gravitation. It is in this sense that I declare it a moment ago to be an isolated fact. The discovery made at the expedition, beautiful as it is, does not, in this circumstance, prove Einstein's theory. We owe it to that great man over there, pointing at Newton's portrait, to proceed very carefully in modifying or retouching his laws of gravitation. This is by no means defending blind conservatism. The spectral shift required is perhaps 100 times, but certainly not less than 40 or 50 times the error of modern measurement. The The solar spectrum can even in this country be observed many times a year, and the matter can thus be decided without having to wait years or centuries for another equally advantageous eclipse. If the shift remains unproven at present, the whole theory collapses and the phenomenon just observed by the astronomers remains a fact awaiting to be accounted for in a different way. But for the math equation part, he's saying that if there's no spacetime curvature to produce the predicted shift, then spacetime isn't curving and you can't attribute any displacement thereof to spacetime. And let's see, continuing on. If you want to propose spacetime as a physical mechanism and not an abstract math concept, you would need to prove it has a physical effect, i.e., the spectrum shift. Continuing on, Arthur Eddington. One word in reply to Dr. Silberstein. When a result that has been forecasted is obtained, we naturally ask what part of the theory exactly does it confirm? In this case, it is Einstein's law of gravitation. It is not necessarily that it is his theory that is confirmed with the underlying assumption that ds is a quantity that can be measured with clock and scale. There still remains the question of what the intermediary quantity ds is, which must be tested by the Fraunhofer lines. Note, ds refers to the space-time interval in general relativity. The subtext of their conversation is about replacing the physical mechanism of gravitational attraction, i.e. mass attracting mass, with space-time curvature. If in fact space-time is a physical entity, spectrum shift would be observed in the Venus observation as stated earlier. In general relativity, the c squared times dt squared is the term in the equation that represents the idea that space and time are not separate, distinct dimensions, but are instead intertwined and connected in a non-Euclidean manner. This means that the geometry of spacetime is curved and distorted by the presence of mass and energy, leading to the phenomenon such as gravity. This is a departure from the traditional Euclidean view of space and time as a separate and flat, unchanging entities. November 7, 1919. Even though the evidence presented the previous day at the joint eclipse meeting was of poor accuracy and presented no accompanying spectral shift observations to confirm the spacetime curvature as the physical mechanism to cause any star displacement, it was announced by Sir Joseph Thomson, president of the Royal Society, stating that the expedition was a success and Eddington had proved Einstein's theory of general relativity. By the time Einstein woke up November 7th, 1919, he was catapulted into stardom and overnight celebrity. British and U.S. media spreading word of how his theory had been confirmed, and the laws of gravitation no longer obey Newton, and they now obey Einstein's spacetime curvature. H. von Kubler, Vistas in Astronomy. So this is now way after the fact. And we're going to see how the evolution of eclipse observations and star displacement has gone since then. H. von Kubler, 1960, Vistas in Astronomy. It should be noted that the deflection predicted by Einstein in 1916 was very small, being that of about 1.7 seconds of arc of a ray of light at the edge of the sun and inversely proportional to the radial distance of the sun. Since no stars for which the measurements were made during the 1990 of the 1919 eclipse were within 2 solar radii of the center, the largest deflection that would have occurred according to the theory would have been less than 0.8 seconds of arc, which for the 343 centimeter focal length of the telescope used by Eddington would have corresponded to about 0.01 millimeters, or 0.000393708 inches on the photograph plate. Even without the spectrum data, the displacement itself is so poor that you can call the entire thing into question on just that basis alone. And actually, later on, this Silberstein guy right here, he ended up finding that when he actually got a chance to examine the photographs thoroughly and stuff, he found that 2 of the stars displaced in the wrong direction that were predicted. So anyway, we'll continue on. Dennis Sima. In Einstein, the man and his achievement, page 39 to 40. The first attempt to test Einstein's prediction was made by a British expedition led by Arthur Eddington just at the end of the Great War. At that time, it was considered very striking that a group of British astronomers should attempt to test the theory proposed by a German. The results of the test were claimed as a triumph for Einstein, and his worldwide fame dates from this event. Ironically enough, attempts made at later eclipses suggest that Eddington underestimated the uncertainties inherent in such a difficult observation, and even today Einstein's predictions has not been tested with the precision one would wish. So just talking about the displacement, they've already forgotten about the spectral shift. That's out the window. They they're just focusing on getting an accurate displacement, and they still can't do it. 1995, John Maddox, editor of Nature magazine. Historically, the most dramatic proof that Einstein was on the right track with his general theory of relativity came in 1919 when Eddington and his associate Crommelin took themselves to the western Pacific to track the total eclipse of the sun of that year. They were bent on measuring the predicted deflection of light from the distant stars lying near the limb of the sun. As the world knows, the prediction was confirmed within the limits of accuracy of the observation. To general applause, Einstein became a celebrity overnight. What is not so well remembered is that the measurements in 1919 were not particularly accurate. The standard error for the measurement was roughly 30%, while the displacement of the images of the two different stars in the field near the eclipsed sun ranged from half to twice the deflection Einstein had predicted. The later eclipse measurements have not been much better, largely because of the difficulties in making an accurate observation from the ad hoc observatories that have to be established. And we got one more from Ian McLaughlin, 1999, Anomalies in the History of Relativity. This is a paper that this guy wrote. If the findings of the eclipse expedition had been announced as being inconclusive instead of decisive in 1919, general relativity would have had to compete with other possible theories such as Gerber's to explain certain astronomical observations, and a better theory might have eventually been found. In the author's opinion, the confident announcement of the decisive confirmation of Einstein's general theory of relativity on November 7th was not a triumph in science, as it is often portrayed, but it is one of the most unfortunate events in the history of the 21st century. What would cause a man to say such a thing? That's crazy. Or is it? I don't know. Let's continue. All right, and to quickly recap on the lack of evidence, we have some potential explanations. Refraction of the sun's corona and or the Earth's atmosphere, distortions in the optical systems made by or caused by the temperature changes during the eclipse, errors in the measurements on the images of the photograph plates, errors in the instruments used to measure the photograph plates, poor visibility conditions and not enough stars to make good comparisons. No spectrum lines that were predicted by the theory were observed. No cause and effect relationship between any perceived displacement and the bending of spacetime can be established. Conclusion. We often hear that math is reality. Despite being able to produce numerous instances to falsify that claim, it is the cornerstone of the relativistic belief system. The mathematical concepts that make up general relativity, Einstein tensors, spacetime curvature, etc., were falsely claimed to have physicality to them. Although there is no physical spacetime fabric, and any bending thereof is conceptual, the evidence put forward requires it to be in fact physical. While there are other possible explanations to explain the phenomenon, only one explanation was given the stamp of approval and seemingly rolled out overnight. We're told fantastical stories about the bending and warping of space-time and how it can become so distorted that it can collapse in on itself, creating infinite curvature to which nothing can escape, not even light. And yet it produces no spectrum shift in the starlight or Venus when they're near the sun. The lack of spectrograph data is the real smoking gun here. Spacetime will later be proven as a physical entity by the Pound-Rebka and Pound-Snider and LIGO and a couple other things in place of the missing data, but we'll get into those in this presentation. And the issues in proving that spacetime is a physical entity will become even more obvious. So, continuing on to gravitational redshift of light. Gravitational redshift is the phenomenon in which electromagnetic waves such as light lose energy as they escape a gravitational field of a massive object. This causes the wavelength of light to shift towards the red end of the spectrum. In the case of gravitational redshift, the energy of light is decreasing, but the speed at which light travels remains constant. The decrease in energy is compensated by an increase in wavelength of the light, leading to a redshift in the spectrum. The decrease in the energy that causes the light to redshift is compensated by an increase in the wavelength so that the speed of light remains constant. Mathematically, it can be stated as E equals h times f, energy times Planck's constant times, energy equals Planck's constant times frequency. As the energy decreases, the frequency of light also decreases, which leads to an increase in wavelength. Since the sun is directly proportional to the wavelength and inversely proportional to the frequency, the increase in wavelength compensates for the decrease in energy, keeping the speed of light constant. In other words, light doesn't change speed, it only changes wavelength and frequency. The wavelength gets longer and the frequency gets shorter, but the product of the two remains constant, and that product is the speed of light. How general relativity explains gravitational redshift and cosmological redshift. In general relativity, there are two types of redshift that can occur: gravitational redshift and cosmological redshift. General relativity defines gravitational redshift as follows: the wavelength of light from an object is shifted at the red end of the spectrum as it travels through a gravitational field. This effect is caused by the fact that the photon of light loses energy as it moves out of the gravitational well. The loss in energy causes the wavelength to stretch. Cosmological redshift: the wavelength of light from an object is shifted towards the red end of the spectrum due to the expansion of the universe. This effect is caused by the fact that the universe is expanding and therefore the distance between objects is increasing. As the distance between an object and an observer is increased, the wavelength of light from that object is stretched, causing a redshift. In summary, general relativity predicts redshift can occur due to the curvature of spacetime caused by the presence of massive objects. It explains redshift due to the energy change of photons as it moves in and out of a gravitational well, which produces redshift. In the case of cosmological redshift, this is due to the expansion of the universe itself. And before we continue on, we'll talk about a few other types of redshift just to give some additional context. Other types of redshift: Doppler shift, caused by relative motion of the source and observer. Time dilation redshift, caused by the difference in rate of time between 2 points in spacetime. Gravitational lensing redshift, caused by the passage of light through a gravitational field which, bending on the path, causes the shift in wavelength. Hubble redshift: light from distant galaxies is shifted towards the red end of the spectrum. This was first observed by Edwin Hubble in the early 20th century, who found the light from distant galaxies which redshifted, which indicated that they were moving away from us. Note: Hubble, even up until his final lecture at the Royal Society, always held open the possibility that the redshift did not mean velocity of recession, but might be caused by something else. Moving forward in the presentation, we'll look at two experiments that are put forward as proof of general relativity: the Pound-Rebka and the Pound-Snider experiments. The Pound-Rebka experiment. The Pound-Rebka experiment, conducted at Harvard's Jefferson Tower, involved emitting photons from a precise known wavelength at the bottom and at the top of a 22.5 meter tall structure. Upon measurement, the photons emitted from the top of the tower were found to have a slightly decreased wavelength, and at the bottom of the tower, at the bottom they were blue shifted, while the ones emitted from the bottom going to the top were red shifted. There are three common interpretations of the Pound-Snider experiment, which are used to support relativity theory, which includes invoking the equivalence principle as support. However, the measurements don't show a need for the principle to be invoked, so let's go over the interpretations now. So one, they'll say time dilation in a gravitational field. General relativity predicts that time passes more slowly in stronger gravitational fields. This time dilation effect is the result of the photon emitted at the top of the tower having a slightly longer time to travel the 22.5 meter distance to the bottom than the photon emitted from the bottom going to the top. Gravitational redshift. Number two, gravitational redshift. According to general relativity, photons lose energy as they escape from a gravitational field. This results in a shift in wavelength of the photon, this results in a shift in the wavelength of the photon to a longer wavelength, which is called gravitational redshift. In the Pound-Rebka experiment, the photon emitted from the bottom of the tower experienced a gravitational redshift when compared to ones emitted from the top. 3. Equivalence of gravitational and inertial mass. The equivalence principle states that the effect on gravity is indistinguishable of that of the effects of acceleration. The Pound-Rebka experiment provides evidence for this equivalence, as the decreased wavelength of the photon emitted from the top of the tower can be seen as being equivalent to the effects of acceleration. Before we continue, it should be noted that the observation of blue shift is what makes distinguishing the gravitational redshift versus the redshift caused by velocity change a problem. Gravitational redshift can only produce redshift. They dismiss the blue shift because they say that it was a small measurement. But the one thing they can determine is that it was the exactly precise amount of redshift to confirm relativity theory. And as we'll see in this next paper, they actually did another experiment 5 years later called this is the paper that they published it, or the title that they published it under, Effect of Gravity on Gamma Radiation, Pound and Snider. So this is the Pound-Snider experiment, and I'll go over what that is now. The Pound-Snider experiment is essentially the same experiment as the Pound-Rebka. However, it produced more accurate results using a 75-foot tall tower. The PRX results came in within 10% of the spectral shift predicted by relativity theory, while the PSX experiment came within 1%. And we'll read some quotes here. To quote the men who conducted the experiment, "It is not our purpose here to enter the many-sided discussion of the relationship between the effect understudy and general relativity or energy conservation. It is to be noted that no strictly relativistic concepts are involved, and the description of the effect as an apparent weight of a photon is suggestive. The velocity difference predicted is identical to that which a material object would acquire in free fall for a time equal to that of the time of flight. Possibility a priori of a discrepancy between the simple theory and experiment in the domain between a few tenths and 1% does not appear large. One aspect may be worthy of mention is that G includes the effect of the Earth's rotation amounting to a reduction from the purely gravitational acceleration by about 0.3%. The view that the local time scale depends on gravitational potential appears to require a coherent source of confirmation. The present experiment is unable to distinguish between the frequency change and velocity changes, for example. It appears as if an experimental comparison of clocks of different potentials would make a more useful contribution to the overall status of the theory." So in their paper, they're saying, look, they don't want any part of saying that their theories, that their experimental results confirm relativity theory, and that even when they do a more accurate test, there's still a blue shift, and they can't determine, they can't distinguish the difference between the velocity shift or the frequency shift, which would be caused by, the curvature of space-time. So to quickly recap before we move on, photons were emitted from the top and the bottom into detectors, and those detectors were used to give spectral shift readings. Examining 3 interpretations of the experiments that are put forward as proof of relativity theory. Although the published works of the men who conducted the Pound-Rebka and Pound-Snider experiments explicitly state that their results cannot distinguish between frequency shift caused by the supposed gravitational redshift, in which the photons would be altered by the curvature of spacetime as they climb out of Earth's gravity well, or if there was a velocity shift caused by the photons experiencing a downward acceleration of 9.8 meters per second squared as they traveled from the top of the tower to the bottom, and in the same respect, if the photons traveling from the bottom to the top experienced a loss in speed equivalent to that of overcoming a downward force of 9.8 meters per second squared. So to rectify this, people have come up with other interpretations that make the results fit relativity theory, so to speak, and we're going to examine those arguments now, taken from this website where the author has compiled the arguments and made refutations for them. So we're going to examine the arguments and his refutations. 3 different interpretations of the Pound-Rebka-Snider experiment results. Time dilation in a gravitational field. General relativity predicts that time passes more slowly in stronger gravitational fields. This time dilation effect is the result of photons emitted at the top of the tower having a slightly longer time to travel the 22.5 meter distance to the bottom than the photons emitted from the bottom going to the top. Gravitational redshift. According to general relativity, photons lose energy as they escape a gravitational field. This results in a shift in the wavelength of the photon to a longer wavelength, which is called gravitational redshift. In the Pound-Rebka experiment, the photons emitted from the bottom of the tower experienced a larger gravitational redshift than the ones emitted from the top. 3. Equivalence of gravitational and inertial mass. The equivalence principle states that the effects of gravity on an object are indistinguishable from those of acceleration. The Pound-Rebka experiment provides evidence for this equivalence, as the decrease in wavelength of the photons emitted from the top of the tower can be seen as being equivalent to the effects of acceleration. All right, so continuing forward in the following slides, we're going to examine these three arguments and possible refutations to them. Number 1. All photons move at c while exchanging energy and momentum with space. Photons shift their wavelengths gradually as they move through the stationary gravitational field. In drawing number 1, photons with a wavelength of lambda equals 1 are emitted. They travel through the suggested gravitational field at a constant speed of c and are impacted by the gravitational field, causing descending photons to gain mass, momentum, and energy from the field, and descending photons to transfer mass, momentum, and energy to the field. As a result, the wavelengths of the photons change gradually as they move through the field. The issue with this explanation is the lack of a well-defined physical mechanism to modify the photon's mass, momentum, and energy without altering its velocity or angular momentum. The only idea that has been proposed is the mathematical concept of a fourth-dimensional substance known as spacetime. This idea explains the shift in the photon's wavelength without relying on the Doppler effect, as all the photons, the source, and the observer are in the same inertial frame, and the photons move at a constant speed of c relative to both. In short, they're saying that climbing out of a gravity well stretches the wavelength and doesn't cause the photon to lose energy. However, this invokes spacetime as a physical mechanism, a well to be climbed out of, breathing life into an otherwise mathematical concept. In drawing number 2, photons are emitted at a constant wavelength of lambda equals 1, but fall towards the Earth like material bodies, causing descending photons to move faster than c and ascending photons to slow down less than c. During their travel time, the ascending photons will slow down by c minus 0.00000076 meters per second, and descending photons will speed up by c plus 0.00000736 meters per second. The resulting red and blue shifts in the photon's wavelengths are due to the changing in velocity relative to the observer. The ascending photons arrive at a velocity less than c, and the descending photons at a wavelength greater than c, causing a shift in wavelength of 2.5 times 10 to the minus 15. The issue with this explanation is that it contradicts the principle of the constancy of the speed of light in relativity theory. According to the theory, the speed of light should be constant independent of the motion of the observer or the source. However, this explanation suggests that the photon in the drawing is moving at different speeds, with none moving at c relative to the source or observer, violating the principle of the constancy of the speed of light in general relativity. Number 3, part 1. Photons acquire shift at source and all move at c relative to an observer. In drawing number 3, it is suggested that gravity slows clocks at the bottom of the tower, causing the emitter to take longer to produce photons with longer wavelengths, while the faster clock at the top of the tower leads to shorter time intervals and wavelengths for the emitter. Although the photons move at c, observers at the top and bottom of the tower would measure their velocity differently due to the varying clock rates. With equal time intervals between photons, the top emitter would produce more photons per second than the bottom emitter. The concept described aligns with the predictions of Einstein's relativity theory. General relativity explains how gravity affects the passage of time and its behavior of objects and the behavior of objects in a gravitational field. The idea that clocks at different heights in the tower run at different rates due to gravity, and that the observers at different positions would measure the velocity of photons differently due to their varying clock rates, supports general relativity's explanation of the relationship between gravity and the fabric of spacetime. This concept also supports the theory of special relativity, which explains that the laws of physics are the same for all observers in uniform relative motion. Special relativity predicts that time appears to run slower in a stronger gravitational field, and that the velocity of light is always constant regardless of the observer's position. Number 3, part 2 continued. Photons acquire shift. You guys get it. Relativity theory predicts atomic clocks run faster at high altitudes than at sea level. However, this can't explain the Pound-Rebka results because the effect would be too small. The only explanation consistent with the equivalence principle is that the clocks running at sea level is due to the Earth's escape velocity affecting the clock's time. Using values from the drawing, the effect of velocity on time dilation is calculated using the following formula. T equals the square root minus v squared over c squared, and that's velocity squared divided by the speed of light in a vacuum. So you take your Earth escape velocity here at that particular height. I'm sorry, that's at the bottom of the tower, so that would be going up, and then from the top of the tower going down, the escape velocity there based on the 22.5 meter elevation. The results show that the difference in escape velocity causes a small slowing of the clock by about 2.17 times 10 to the negative 21, much smaller than the amount that was measured by Pound-Rebka, which was 2.5 times 10 to the negative 15. This suggests that the effect of time dilation is too small to account for the Pound-Rebka results by a factor of 1 million. Conclusion: the equivalence principle isn't measured in this experiment because its effects would be too small to perceive, so it doesn't support the claim that the experiment supports relativity theory. And just some further notes here. Escape velocity is usually defined as the minimum velocity required for an object to escape a gravitational pull of a celestial body. In this context, escape velocity is being used to describe the minimum velocity required for an object at a particular location on Earth's surface to escape the gravitational pull. And there is, this is the effect that they detected, and this is what the effect of time dilation would be, if it was to be present, and it's way too small for them to measure. The escape velocity difference between the top and the bottom of the tower causes a redshift of only 2.17 times 10 to the negative 21, which is much smaller than the 2.5 times 10 to the negative, or times 10 to the minus 15 shift, which was observed in the Pound-Rebka experiment. The escape velocity difference between the top and the bottom of the tower cannot fully explain the Pound-Rebka experiment. Afterthoughts on phase shift. The Stark effect and Zeeman effect. The Stark effect states that electric fields, such as charges in the environment or currents flowing through the conductors of the equipment that's being used to make the detections and measurements of the photons, can produce redshift via splitting the absorption lines. Similarly, there's an effect called the Zeeman effect, which is basically the same thing but with magnetic fields. The reason for the split is that electrons changing shells move faster if they're going with the field and slower if they're going against it. When the emitting photons of the faster electrons emit a blue-shifted photon, the slower ones emit red-shifted photons. Since these could travel in any direction, an observer at a distance will get both varieties. Thus, the single emission line has been split into two lines. Corollary to this rule for the emission is during the absorption that the electron must fight against the electric field and can only be absorbed by a red-shifted photon, and the electron being accelerated by the field can only be absorbed by a blue-shifted photon. For precisely the same reason, we should expect spectral lines to be split by a gravity field. Electrons moving upward and downward in the field should absorb only red-shifted and blue-shifted photons, respectively. These effects could have also impacted the results of the Pound-Rebka and Pound-Snider experiments. Continuing on, we're going to get a visual representation of what spectral shift due to magnetism looks like. And we'll let Ken Wheeler take it away here in a second. So let me give him a little introduction. Ken Wheeler demonstrating magnetism as a physical mechanism for phase shift in light and with the effects of relative motion. When light travels through the medium of a refractive index different from that of air or a vacuum, it can experience electromagnetic retardation, which is caused by the refractive index, which is caused by the interaction of the light with the electric and magnetic fields of the medium. This can lead to a change in the wavelength of light, resulting in phase shift. When a magnet is placed over a ferrocell, the EM field created by the magnet causes a phase shift in light that's passing through the ferrocell. The LED lights around the ferrocell split into a red and blue shift at the opposing ends of the magnet's north and south pole, with the north pole producing a red shift and the south pole producing a blue shift. Moving a ferrocell over the magnet changes the polarity, causing the north pole to produce blue shift and the south pole to produce red shift. This is a very important distinction because spacetime has no refractive index. The mechanism by which relativity claims that phase shift is induced is because of an object's gravitational effect on spacetime, causing it to bend and warp, and it's the light traveling along that curved path that produces the effect. If spacetime curvature was ultimately the cause of any star displacement, the redshift would specifically match relativity theory's prediction in the 1919 eclipse or any other subsequent observations of Venus throughout the year. No spacetime redshift has ever been demonstrated or observed in these observations that would establish a cause and effect relationship with light being displaced by spacetime curvature. All right, and with that being said, we're going to watch Ken Wheeler's demonstration.
Blue shift. EM retardation, the disparity of motion. Here we have zero motion and we have a phase shift, a blue phase shift and a red shift, which exists at a ratio of 5 to 1 or 1 to 5, depending on how you look at it, which is actually an egg shape. It's a perfect egg shape. If you're able to cut an egg, dissect it in half, we'd have the pointy tip up here, which exists at a volume, a ratio of 1, and down here the larger, fatter section of the egg, which exists at a ratio of 5, so 5 to 1, which together is 5 squared, which is 2.1618, so on and so forth. So how am I able to simulate on this tiny, tiny little scale, moving about 1 mile an hour, stellar redshift and blue shift? The only thing I have to shift is this magnet, relative to the lights here. Let's say I'm an observer on a planet over here, and this is a star. Let's say I'm another observer on the opposite end over here. Let's recreate redshift and blue shift. Remember now, this is red and this is blue. But how can I shift that? Relative motion to the disparity of the electricity, i.e. light, which is a coaxial circuit, transverse electrical magnetic, longitudinal dielectric. Let's show you phase shift. Now look closely and I'll explain it. You see how this is blue now? As it was approaching, it went to blue shift. If I move it away, let's just look at this one pole only. Let's ignore this pole over here, okay? You notice that this redshifted now? Let me move this closer to a person over here. Let's say there's a person on a little planet over here, and this is a star. Okay, now it's redshifted. Let's move the star closer to this person over here. You see how this blue shifted? Let's move it away and watch this blue, which is bluish green, but it's still blue shifted, turn to red. Redshift. Blue shift. We're only looking at this pole over here. A second. I think I had a little power outage there. There we go. Blue shift. Redshift. Redshift, moving away from this relative point. Now let's take a look. Let me check my power connection here. Let's take a look at the other pole. Hold on a second. There we go. Sorry about that. Let's take a look at the other pole over here on the right side. Let's orientate my magnet exactly. Okay, let's wait for it to appear. There we go. Let's take only a look at this. Blue shift relative to this person over here. Let's say this point over here. Blue shift, as it moves away relative to this point, we have red shift. You notice how it shifted to the red? Now watch it shift again. Remember, only looking at this pole on the right side of my finger. Okay? Red shift, blue shift. Red shift, blue shift. Inverse to the other pole. Look closely. Nothing has changed other than disparity of EM retardation. It has nothing to do with space. It has nothing to do with time. It is EM phase shift disparity, or EM retardation. This is also the differential that is programmed into every global positioning satellite relative to its motion. This has nothing to do with Einstein, has nothing to do with general relativity, has nothing to do with quantum mechanics. The universe is purely dielectric and magnetic. If you want to think of it as electrical, that's fine.
Pound-Rebka-Snider conclusion. The well-established phenomena of Doppler shift due to relative motion has been reliably confirmed through numerous experiments in physics. However, attributing the blue shift and red shifts observed in the Pound-Rebka and Snider experiments to a gravitational field and spacetime curvature negates the validity of Doppler shift and instead relies on the equivalence principle, which lacks empirical verification. This principle is frequently imposed as a philosophical assumption prior to conducting experiments, overriding any results that may contradict human intuition. As seen, relativistic enthusiasts will interpret any experiment in any way possible to support relativity theory, up to and including ignoring known factors that will affect the measurements and experimental results, and even outright ignoring known causes to phenomenon such as Doppler shifts, the Zeeman effect, the Stark effect, etc., and attributing them to the bending and warping and stretching of spacetime, which is a concept that has no physical meaning and is only expressed mathematically as a metaphysical solution to observable phenomenon. The Zeeman and Stark effects could have impacted the results, altering the measured phase shift. To this day, there is no terrestrial experiment that has ever been done that provides proof of spacetime as a physical mechanism that expands, contracts, or that can cause phase shift in light. Okay, so if we remember back to the Pound-Rebka and Pound-Snider experiments, in the last paper that they published, quote, "It appears as if an experimental comparison of clocks at different potentials would make a useful complementary contribution to the status of the overall theory." So again, reiterating that their experimental results didn't confirm anything because they couldn't differentiate between frequency shift and velocity shift. So they suggest that they should use some really accurate clocks at different elevations to determine, the effects of space-time curvature and gravity fields and all that. So insert time dilation. The Hafele-Keating experiment was conducted to test the predictions of Einstein's theory of special relativity. In the experiment, the researchers compared the frequency of light emitted by traveling atomic clocks with that of stationary clocks. They also measured the frequency of the cesium atoms in the clocks to determine the time difference between the clocks. The researchers used spectroscopy to look for the spectrum shift of the light emitted by the traveling clocks relative to the stationary clocks. The amount of redshift observed in the spectrum of light was used as an indicator of the difference in velocity between the two sets of clocks, and this difference in velocity was used to calculate the time difference between the clocks. A higher redshift indicated a greater difference in velocity and a greater time difference between the clocks. Performance and results of portable clocks in aircraft. The original data from 1971. The original data from the Hafele-Keating experiment shows that 3 of the 4 clocks were unreliable and had significant variations in their drift rates, which should have been steady in order to make accurate measurements. Table 1 shows the drift rates of the clocks before and after the eastward and westward test. And I have them color-coded here. Before and after is yellow, the difference is red, and the mean is blue. The conclusion from the data is that huge swings in the drift rates made the results of the experiments unreliable and inconclusive. The accuracy of the clocks would have had to have been better by 2 orders of magnitude in order to reach a meaningful conclusion on the test. Take note of the mean values, as we'll be comparing the original recorded results before and after the post-analysis and consolidation that was conducted, which brings the results more into line with a published paper they did the following year. Hafele-Keating published data in Science magazine after the post-analysis and consolidation in 1972. Here we compare the original data and the data after the post-analysis and consolidation was done. In their published paper, it is mentioned that the corrections were made to include the relevant information of flight speed and altitude, not accounting for taking off and landing altitude changes, moving the clocks, etc. And suddenly the results are brought in line with the predictions of relativity theory. It should be noted that no source of exactly what was changed or how it was accounted for can be found. Relativity wins again. So on the eastward trip, relativity theory predicts that the clock should lose 40 nanoseconds plus or minus 23 nanoseconds. And on the westward trip, the clock should gain 275 nanoseconds plus or minus 21 nanoseconds. The original recorded data wasn't very much in line with the predictions. And after the massaging of the data for the post-analysis and consolidation, which we have no idea how exactly, what exact math was done to get these calculations, they were brought more in line with the relativistic predictions. And now relativity wins again. Some of you might be saying, oh, that's cool that they did east and west trips, but what about north and south circumnavigation? Well, they said that the north-south circumnavigation wouldn't be necessary because the Earth's magnetic field would be too strong and it would impact the results too much. Even though that they claimed that they triple shielded the clocks and, took every countermeasure to, minimize the effects of things like the Zeeman effect. But anyway, I think it's probably because north-south circumnavigation is impossible. Because why would you not want that data to also compare, and it doesn't exist at all. They just decided not to do it. And I think at the time of the trip, the military actually sponsored this whole thing, and it cost about $9,000 in total to do this experiment. What's another $9,000? Hafele-Keating conclusion. Extraordinary claims require extraordinary evidence, and the evidence and interpretations of the Hafele-Keating experiment is anything but extraordinary evidence. You can approach the results of the experiment from various angles to show that the so-called relativistic effects attributed to it can be accounted for within the confines of natural processes. Time dilation is a physical effect of various factors which I will now list. Electromagnetic retardation, changes to the medium in which light is traveling, i.e. electric or magnetic. Motion can cause atomic clocks to become out of sync. Even in stationary lab settings, they drift out of sync. It just happens faster when they're moving. Moving the devices themselves, the clocks were transferred on and off plane 6 times, and they were placed in commercial seats. They weren't level. They weren't, any turbulence that happened, during the flight. All that stuff could have affected the results, and how they finessed the post analysis and consolidation. They could have just, like, we have no idea how they accounted for any of these so-called effects. So data changed to fit the relativistic predictions of time dilation. The prediction itself was extremely small and could be attributed to by other factors. With all this taken into consideration, supposedly only one clock gave a decent reading and had a predicted drift in line with the predictions. It is presumptuous to say that time is affected rather than the physical mechanism of the devices being used is falling out of sync due to natural phenomena. To put it in perspective, to believe the Hafele-Keating experiment supports relativistic time dilation, then you must also believe that a man who lives on the top of a mountain lives slightly in the future compared to someone who lives at sea level, despite there being no way to quantify that. I'll leave a link to the sources below, and you can dive into the technical aspects of the experiment and interpret them for yourselves and draw your own conclusions. There are many to choose from. Experimental evidence for general relativity, gravitational waves. Gravitational waves. Gravitational waves are the ripples in the fabric of space-time caused by the collision of massive objects, i.e., in this case, black holes. They were predicted by Einstein's theory of general relativity in 1915 and were detected in 2015, exactly 100 years to the day of Einstein's prediction. By LIGO, the Laser Interferometer Gravitational Wave Observatory. The detection provided direct evidence of the existence of gravitational waves and confirmed a key aspect of Einstein's theory. LIGO was designed to detect gravitational waves. It consists of 2 detectors, one in Hanford, Washington, and the other in Livingston, Louisiana, which use laser interferometry to measure an extremely small distortion in space-time caused by passing gravitational waves. The laser shoots a beam down long tubes, and any warping of space-time caused by the traveling of a gravitational wave will change the relative distance between the beams, causing a detectable change in the interference pattern. By comparing the data from the detectors, LIGO can identify and measure the signature of gravitational waves passing through the Earth. And I'm going to play the press announcement of LIGO's detection of GW150914, which is the name of the gravitational wave that they say that they detected.
Ladies and gentlemen, we have detected gravitational waves. We did it.
Woo! Woo! We did it! Woo! All right. So they detected gravitational waves. They did it. And that was their press announcement. LIGO. On February 11, 2016, the LIGO Scientific Collaboration and Virgo Collaboration announced the first confirmed observation of gravitational waves from colliding black holes. The gravitational wave signals were observed by LIGO's twin observatories on September 14, 2015. This confirms a prediction of Einstein's theory of general relativity and provides the first direct evidence of a black hole's merger. What is not mentioned here is the subtlety of giving physical manifestation to spacetime via the medium which rippled in the first place to allegedly cause the interference pattern that LIGO says that they detected. It's also served as confirmation for the existence of black holes, and actually multiple different types of black holes, because the black holes that were detected here are different from the regular type that they quote-unquote detect using the Schwarzschild radius. It's also served as confirmation for the existence of black holes, as 2 black holes had to collide 7 billion years ago to produce the wave that was detected. It also reifies their timeline of billions of years. And not only that, but all of this was predicted by Einstein and/or derived from his equations that describe space-time curvature. Integrity issues at LIGO. And this article is taken from LIGO's own website. The collaboration knew that the detection could be a blind injection, a fake signal added to the data without telling the analyst to test the detector and the analysis. Nonetheless, the collaboration proceeded under the assumption that the signal was real and wrote and approved a scientific paper reporting the groundbreaking discovery. A few months later, according to plan, it was revealed that the signal was indeed a blind injection. While the scientists were disappointed that the discovery was not real, the success of the analysis was a compelling demonstration of the collaboration's readiness to detect gravitational waves. Wow, what an incredibly positive spin on the fact that all these guys went to work for months, years, and got rickrolled. But, it was a great display of their willingness to detect the thing that their paychecks depend on. Great. Before we get into the closing here, the gravitational wave that they say that they detected is titled GW150914. And this wave was detected while the system wasn't fully operational. It had just come up, it hadn't even been cleared from maintenance yet. It was just coming off of a reboot of a test run. And before the system was operational with its safeguards that prevent, like false positives and things, before that system was activated, it made the quote unquote discovery, and they went and ran with this and then couldn't figure out that it wasn't even real. So, and this is $1 billion operation to build this thing, and their own scientists couldn't tell if it was real or not. So I'm not going to waste any more time going in depth on gravitational waves and how they're derived and how theoretical it is and all that. Their own people don't know. So we're going to move on to the conclusion. How math became reality. Conclusion. That's the historical and classical experimental evidence put forward as proof of relativity theory. In my opinion, there was a concerted effort to push relativity theory into mainstream acceptance. Someone or some group out there realized that they could use the space-time curvature framework of interpretation to hijack the sky clock and natural electromagnetic phenomenon by producing a way to explain them by using space-time metaphors backed up by math. The term space-time or space-time curvature is fictitious doublespeak. It has never been experimentally demonstrated that relativity theory is anything more than a mathematical framework. Space-time has no physical attributes. It cannot distort time or alter the path of mass or massless objects as they travel in a geodesic along said non-existent curvature. Some people believe that relativity theory has been proven correct because its predictions have been proven correct many times. There are other ideas like Lorentz's ether theory that also make similar predictions. The problem with the theory of relativity is that it uses math to make successful predictions, but the way it explains time and space doesn't make any sense and even contradicts what we know to be true. The root cause comes from the shift from Lorentz's ideas of absolute time and a variable speed of light to Einstein's idea of relative time and a constant speed of light. The Sagnac effect shows that the speed of light can be different based on where you're looking from, and this can make it seem like time is moving differently. The real gravy between the two systems is Lorentz's system implies that the stars, planets, galaxies, and other celestial objects are closer and in a denser medium, while relativity theory is essentially the inverse of a closer and denser ether theory, which allows for a much wider range of interpretations when it comes to distances and sizes and the nature of the medium of the so-called vacuum of space. The reason mainstream science can tell us that a photon traveling for 13.7 billion years to reach our eyes has traveled 86 quintillion 600 quadrillion miles and keep a straight face is because of that inversion and the constant speed of light and relative time. Experimentation should dictate the advancement and verification of theories rather than theories dictating the outcomes of experiments so that the data can be selectively used to reify the theory. And that's the conclusion on the classical experimental evidence put forward in support of relativity theory. The perihelion precession of Mercury, the deflection of light rays, gravitational redshift of light, and gravitational waves. All sources are available for download at the MediaFire link provided. Thank you for watching the presentation. If you have any questions or comments, you can find me on the YouTube. You could find me in the YouTube comments on this video or on the Telegram or Discord linked in the presentation. And as Jaren from Jarenism says, remember to do your own research because when you do, you'll never believe this crap again.